In this video, I'm going to focus on the terms and variables associated with kinematics in one dimension. Start with our length measurement terms. There are four of them. They're on your screen. Know that all of them are measured in meters, and if you're started at anything but meters, you'd want to convert back there. Position is the variable x. It defines where an object is. Starting position is where the object was when time was equal to 0 seconds. And often the x will have a little O next to it that just indicates 0 seconds or at the start. Distance is the variable d. We define it as how far an object traveled, and this is regardless of direction. So distance is a scalar. Displacement, triangle x or delta x. This is the change of position of an object, and you could solve for it quickly by subtracting the final position by the starting position. This quantity, direction, does matter. It would be classified as a vector. In application to everyday life, every car is equipped with an odometer, which shows the number of miles that the car has traveled throughout its lifetime. Many of these are digital now, but a while back they were just these scrolling numbers. That's the picture I have for you. But regardless, the question is, which of these four previously discussed length measurements do you feel the odometer would be representing? The answer would be the distance. This meter shows how far the car traveled. It does not show direction. If it did show direction, you could have your car go backwards and you'd see this meter tick downwards, which does not happen. An example more specific to what you might see in a physics class. Here we're following the orange vectors. We see it going to the right. The student's going to run 100 meters to the east, to the right, and then they're going to turn around at that 100-meter marker and head back towards 50 meters back to the left. The goal is to fill in the table at the bottom right, coming up with 4 different numerical answers. If you want to pause the video and try this yourself, I'll walk you through each here in a minute. All right, let's begin with starting position. You can see the beginning of the first orange vector starts here at a position of 0 meters, so we'll indicate that as our start. Position infers the final position or the ending position after all of the legs of the trip happened. And you can see the final orange vector ends here at 50, so we'll indicate that as our ending spot. Distance is how far we traveled regardless of direction. So regardless of which way they point, we ran 100 meters, then we ran 50 meters. So in full, we've run 150 meters. Displacement is the calculation of the subtracted difference between ending and starting position. So we ended at 50, we started at 0, so we're going to end up with 50. And because displacement is a vector, we'd want to add in direction as well. We started over here at 0, we ended over here at 50, we were displaced to the east. Next, we'll look at our rate terms, or things related to how fast we're traveling. And in real life, we measure this in miles per hour, but in physics classes, we want to be in meters per second. 2 pairs of 2 in this list. We've got speed versus velocity, and also instantaneous versus average. Let's start with instantaneous speed. This is how fast an object is traveling at any instant, indicated with a capital S as the variable. Instantaneous velocity, again, is at an instant, but now we're factoring in direction as well as how fast we're moving. Average speed is, again, how fast, but now over a time interval. And average velocity is how fast over a time interval, but also considering which direction is for traveling. 2 equations to help us with those final 2 terms, average speed and average velocity. Average speed, we're going to relate to distance because both of those are scalars. Direction doesn't matter. So if you want to find the average speed, go with distance over time. Average velocity is a vector, and so is displacement. So we'll compare those as well. So displacement over time would help us with average velocity. Another real-world application, another meter in your car. This one helping us with how fast the car is traveling. The question is, of the 4 previously discussed rate terms, which one is this meter showing? The answer would be instantaneous speed. There's 2 reasons for this. This meter tells us how fast we're going and does nothing to tell us what direction we're traveling in. So we'd rule out velocity for that reason. There's also no time interval over which this measurement is recorded. It's at any instant. When you look down at it, it's telling you how fast the car is moving right then. So we're going with instantaneous speed for this application. Finally, acceleration is a term we're going to want to know. This is the rate of change of instantaneous velocity for an object. So we need velocity to be changing, speeding up, slowing down, and this is measured in meters per second squared.